Hi, everybody. We're talking about right triangles today and Pythagorean triples. Pythagorean triples are special sets of whole numbers that make the Pythagorean theorem true. So if you put any of these into a squared plus b squared equals c squared, they're going to make that equation true. And they really are worth memorizing. They come up over and over and over again. So if we use any of these to prove that it's true, we can do 3 squared, this is squared, plus 4 squared equals 5 squared. That's definitely true because 9 plus 16 equals 25. We can go to another one and see if that works. 5 squared plus 12 squared equals 13 squared, which is true because 25 plus 144 equals 169. And we can even go over to a really big one. We could do 9 squared plus 40 squared equals 41 squared, because 81 plus 1600 equals 1681. You can also graph these, so it's going to be really hard for me to do this here, but if we, on your paper, if you printed this out, you could do 7 by 24 by 25. So 7, 24, 25. Remember that biggest number is always going to be your hypotenuse. Or you could graph 5, 12, 13. So 5 squared plus 12 squared equals 13 squared. Or the really common one, 3, 4, 5. 3, 4, 5. That's the one that's going to come up most often. You really, really, really need to memorize that guy. All right, well, let's erase this. Go on to the next part. Use some of these same numbers. Use a scale factor to make 3 other sets of Pythagorean triples. So it's kind of already done for you up at the top, but if I use 3 squared plus 4 squared equals 5 squared, and then I multiply everything by 2, that would give me 6 squared plus 8 squared equals 10 squared. All of them work that way. You could take the 5 squared plus 12 squared equals 13 squared and multiply that by 3. So your scale factor would be 3. So 3 times 5 is 15. 15 squared, 3 times 12 is 36. 36 squared equals 13 times 3, which is 39 squared. And if you did that, because you know that the 5, 12, 13 works and is a Pythagorean triple, then the 15, 36, 39 also works. A couple more things for notes. Remember, if you have sides and you want sides, you're going to use Pythagorean theorem. If you have sides and you want angles, you're going to use trig. And there should be little negative ones in here, right? The negative one is like the little degree symbol. If you're looking for the degrees, then you're going to use inverse trig. Let me erase this for a second. You can also use the trig functions. So sine x, if I make this x, then the opposite is 5. So the opposite is 5. And the hypotenuse across from that right angle is 13, which means the adjacent is 12. Okay. Just a little quick review about right triangles. So Pythagorean theorem will give you sides, trig will give you sides from angles, and then inverse trig will give you angles from sides. We're going to practice all of those in here today. Oops. There we go. Special right triangles. We talked about this in trig. Hopefully you remember. We've got x, 2x, and x on the square root of 3. And here we've got x, x, and x on the square root of 2. Remember those charts? I'm going to make one over here. We've got 30, 60, 90, x, 2x, x on the square root of 3. And then over here, we can do 45, 45, 90, x, x, x on the square root of 2. Okay. So if we solve for this, we know opposite the 30 is the x. Opposite the hypotenuse is 2x. And then this is x on the square root of 3 opposite the 60 degrees. So if 2x equals 14, then I divide by 2 and x equals 7. So everywhere we see a 7 or an x, we can replace it and put a 7. Everywhere we see an x, we can erase it and put a 7. Same thing over here, across from the 45 is x, so 8 equals x. So the other side, because it's isosceles, is going to be 8, which means this is going to be 8 on the square root of 2. If you can memorize this pattern and get good at using it, you will save yourself so much time on the SAT. Remember, the SAT is timed. Our SOLs are not. That's one of the reasons that it is such a frustrating test, because we're just not used to doing timed things. Same thing with this one. They're just going to get a little bit harder. This is the 30 degrees. So this is x. So 2x is going to be 2 times 5 on the square root of 3. You multiply those coefficients, and then w is going to be 10 on the square root of 3. And over here, this is going to be x times the square root of 3. This whole thing is x. So when I replace that, I have 5 on the square root of 3 times another square root of 3. Just like here, we multiplied the two numbers outside of the radical. Here, we're going to multiply the two numbers inside the radical. So 5 square root of 9, which is 5 times 3, or 15. Over in number 4, you basically do the same thing. We got 45 and 45, so our two legs are x. This is x on the square root of 2. This is why we had to learn how to rationalize. So if 10 equals x on the square root of 2, divide by the square root of 2, divide by the square root of 2. Can't have a radical in the denominator, so you essentially have to multiply by 1 to get rid of it. So 10 times the square root of 2, and then square root of 2 times the square root of 2 is square root of 4, which is 2. So that's going to be 10 square root of 2 over 2. This is just like a slope. We can reduce it. So 10 divided by 2 is 5, 5 on the square root of 2. So OB is 5 square root of 2, and BY also 5 square root of 2. Go on to the next question. See if you can do those while I get this set up. We're moving on to page 3. This one is definitely harder. Erasing takes so much time. All right. Number 5. I'm going to be able to see the whole thing.